Good morning and welcome to all of you to this session of this course. I already discussed earlier that there is an phenomena known as slip, which is very important. Slip. Now I tell you what is slip. When a fluid flows through a curved vein and the vein rotates, what happened? Because of the combined effect of the tangential flow and the radial flow past the curved veins, there is a difference of pressure in two sides of the vein. In the leading edge, the pressure becomes high, the fluid is decelerated, and in the trailing edge, the pressure becomes less and the fluid is accelerated, and there becomes a small recirculatory flow. Probably you can remember which we discussed in a case of centrifugal pump. Here let us discuss here. Now if we consider this moving in this direction, in this side for example, there is a positive pressure. Positive means higher pressure, and this side the pressure is lower. That means this is because of the movement, this rotation of the blade and the flow in past the blade in the radial direction. Because of the blade curvature, it moves like that, and at the same time the fluid flows in the radial direction. As a combination of that, the fluid element here is decelerated in the leading edge. This is the leading edge of the blade, and fluid here is accelerated. So what happens? There is a higher pressure here, there is a lower pressure here. So what happens here? I show you, it gives rise to a recirculatory flow in this direction. This is the higher pressure region, this is the lower pressure region. And what happens? This recirculatory flow, if you see this passage, this happens same way in all passages, makes a non-uniform distribution of velocity, and that non-uniform is a skewed one. That means this makes a distribution like this. This was discussed earlier also. This makes a distribution like this. The velocity distribution becomes much skewed. Here the velocity becomes, on this side between this passage is high, here this is low. So this way the velocity distribution changes. So as a whole, what happens? Because of this small recirculatory flow, due to the difference in pressure from the leading and the trailing edge, there is a change in the direction of the velocity of the fluid relative to the blade. So this results in this way. That means we wanted that the fluid will go in the radial direction, rather it will move in this way. That means the direction of the fluid relative to the blade is changed like this. So this is velocity relative to impeller. This is this velocity triangle. Here you see this velocity triangle, this triangle, this is the triangle. So this is now the VR2. So this is VR2, and therefore what happens? If this becomes VR2, then this is the change velocity triangle. It is just similar, if you recall what we discussed in case of centrifugal pump. So what happens is that in that case, this is the tangential component of the absolute velocity. Now if you compare these two, this U2, this is U2. Obviously U2 remains same. U2 depends upon the rotational speed and the outer radius of the impeller. Okay. So therefore for the same U2, at the impeller outlet, V2 is reduced and this component is reduced from that of the U2. So therefore as a result, what we get, VW2 is less than U2. In this case it was VW2 U2, because the relative velocity is radially outward. Here the relative velocity is like this. It is the similar thing what happened in case of centrifugal pump. So this is the slip, but you have to know the fluid mechanical principle of slip. It is because of the blade curvature and the rotation of the blade, the motion is being imparted to the blade. At the same time the fluid flow past the blade on the two sides of the blade, leading edge and the trailing edge, which creates, it is a sort of a circulation combined with a linear flow which is in the radial direction, which creates this type of difference in pressure and a local recirculatory flow, as a combination of this with the radial flow outward makes a skewed non-uniform distribution of the velocity, which finally results in this type of velocity triangle where we get the relative velocity at the outlet is not radial, as a result of which finally we get VW2 is less than U2, which means that if we see the energy transfer, so therefore this will be now VW2 is U2, so this will be now actually E by m, if VW1 is 0 is VW2 U2. Since VW2 equals to U2, we wrote is U2 square. But now if VW2 is not equal to U2, so it will not be U2 square, and if VW2 is less than U2, then it will be less than U2 square. Here a terminology is there, defines slip factor. A factor is defined known as slip factor, which is symbolized as sigma. I did it for centrifugal pump also, which is here defined as VW2 by the ratio of the outlet welding component or the tangential component of the fluid at outlet divided to the tangential speed of the rotor at the outlet. So, if slip factor is defined like this, then in terms of the slip factor we can define that the energy per unit mass is then sigma U2 square, and sigma is less than 1. Sigma is less than 1, and therefore we see because of this slip a less amount of energy is being imparted to the fluid as compared to that if there could have been no slip. So, how slip will increase? Now, one thing I tell you again and again, which I told you while discussing the centrifugal pump, that slip is not a consequence of fluid viscosity. Slip is a consequence of the motion of the fluid, the rotation of the fluid by the action of the blades. Even the fluid is inviscid, the slip will occur. So, therefore, be careful, the slip phenomena is not because of the fluid friction, though the slip ultimately reduces the energy from what we could have got if there was no slip. There is a formula to find out slip. So, this formula is known as Stanid's formula. Stanid's, from a potential flow analysis, expressed this slip like this. You can get some idea from here, 0.63 pi by n, where n is equal to number of blades, where n is equal to number of blades or vanes. Now, you see here very much that if the number of blades, so therefore, you see if the number of blades increases, what happens? Sigma increases, the maximum value is 1. When number of blades tends to infinity, sigma tends to 1, there is no slip. That means, if you make small streams or more number of blades, infinite number of blade passages, then slip will be totally reduced, almost reduced. On the other hand, when number of blades is decreased, slip is decreased, which means slip will be much lower than 1, and there will be a much reduction in the energy imparted to the fluid. Okay. So, therefore, due to the slip, finally, the energy imparted per unit mass is given by sigma U2 square, where U2 is the outlet tangential velocity of the impeller or impeller blade, and sigma is the slip factor. Now, if we consider other losses, mainly the mechanical frictions, okay, and the windage losses, this type of losses if you take care of, then you have to give more amount of work as given by that expression, and therefore, the energy per unit mass is written by making another term as a product, that is psi, which is known as power input factor. Psi is known as power input factor. Okay. Power input factor. So, this is known as power. That means, this takes care of frictional losses, the disc frictions, the frictional losses, the disc frictions windage losses, all these things is taken care of by the power input factor, which by physical sense will be greater than 1. Definitely, that means this will be greater than 1. That means this will be the energy requirement of the machine. So that out of this, this will be imparted to the fluid, which will exhibit the slip phenomena. And this value of psi usually lies between 1.03 to 1.05 like that. So, therefore, finally we arrive at this expression that energy per unit mass given to the fluid is sigma psi sigma u2 square. This is the amount of energy given to the fluid. Now, let us find out in terms of the pressure rise. Let us do some thermodynamics. Let us consider now, here again I come here. Let us consider this will be better here. We are not going unnecessarily to this complicated figure. Let us see that this is the inlet to the impeller section 1. This is the outlet of the impeller section 2. This is the outlet of the diffuser section 3. Now, let us consider this way that section 1 to 2, when the fluid flows, it gains the energy. So, the energy is being imparted here, whose value is, just now we have written psi sigma u2 square. This is the energy required, but actually fluid gets this energy sigma u2 square. Psi sigma u2 square is the total energy required, part of which is lost in friction. So, therefore, this energy is being imparted in the fluid only here. So, 2 to 3 there is no energy given. So, total energy between 2 to 3 remains same. There is no energy given to the fluid. There is no energy interaction. So, therefore, what happens, the energy level at 2 and 3 remains same, but there is a difference in pressure between 2 and 3 because the pressure rise takes place in the diffuser. So, now if you give this 1, 2, 3, now if we with this, can you see this 1, 2, 3? Yes. Then we can draw a, in thermodynamics, the TS diagram. Okay. Let us consider now the pressure here is, total pressure is P1T, and at the end the total pressure is P3T, and we show these things like this, P1T, and we show this thing P2, these are diverging lines, P2T. What is total pressure? Total pressure is the static pressure plus the stagnation plus the velocity pressure. That means the pressure velocity head equivalent, pressure equivalent of the velocity head or the kinetic energy. Now, I will not show you here, it will be difficult. Now, 1 is the inlet of the impeller, 2 is the outlet of the impeller. Now, you see one thing, that what is this P1, P1. Now, stagnation pressure, total pressure, I am just recalling again. Total pressure is the static pressure Ps plus rho V square by 2. For any fluid stream, if you make the velocity 0 by some way, for example, you make the area infinitely large. So, therefore, if you write the Bernoulli's equations at 2 points along a streamline, then you can get that Pt, when the velocity becomes 0, then Pt equal to total pressure. That means the pressure there equal to Ps plus rho V square by 2. And you can write Bernoulli's equation when there is no energy added from outside, okay, and there is no dissipation taking place, no fluid friction, no dissipation. So, therefore, under ideal condition for an inviscid fluid, this is synonymous to an isentropic flow, that the fluid is brought to rest. Then we can write, for example, if this is the point 1, if this is the point T, for example, where the total pressure is obtained. So, therefore, P1, that P1 is the Ps here, let this is S, Ps is this pressure here, plus Ps by rho plus V square by 2 is Pt by rho plus 0. So, which gives rise to this. That means the total pressure is obtained by writing the Bernoulli's equation, means that the fluid is decelerated isentropically. Isentropically means without any internal irreversibility. without any heat transfer, therefore external irreversibility is also not there, purely reversible way, and without any other energy added or taken out. So therefore this is the concept of the total pressure. So this is the total pressure. Now let us consider the stagnation temperature. What is stagnation temperature? Similar to that, the concept of stagnation temperature is the temperature which is being gained if a fluid stream is brought to rest, but there is no concept of reversible way. That is, you can bring to rest even in consideration of the friction, because the total energy is conserved. For example, I just give you the recalling this stagnation temperature concept, that 1 and T. The similar way, if you do that, a fluid stream is being retarded from a point 1 to a point here T, and if we write this energy equation, then steady flow energy equation H1 plus kinetic energy V1 square by 2, and if we consider that it is done adiabatically, that means no energy interaction either in the form of heat or in the form of work takes place, then we can write H2 plus 0. So this equation is the steady flow energy equation where we neglect the change in potential energy. So there is no other form of work transfer either from outside or from the system, outside to the system or system to the outside. Then therefore for this control volume system, a steady flow energy equation gives rise to this, where friction is not coming into picture. So therefore here this H2, that H1 is what? Cp into T1. This is the section 1 for example, plus V1 square by 2, and H2 is Cp into T2. So this T2 is corresponds to the stagnation temperature of T1. You understand? So therefore a stagnation temperature, if you write the Tt, is equal to what? It equal to Ts. This is known as the static temperature, plus V square by 2 Cp in general. That means this is the velocity or kinetic energy equivalent, velocity head or kinetic energy equivalent of the temperature. This is kinetic energy equivalent of the pressure. This kinetic energy equivalent of the pressure is realized if this is done in a reversible way without any dissipation, absence of friction. But this is purely energy conversion. So therefore this is the temperature, this is the velocity equivalent or the kinetic energy equivalent of temperature added with static temperature gives the total temperature, where the fluid velocity is reduced to 0 without any restriction whether friction is there or friction is not there. This is because the friction takes care of the pressure, but here the friction does not come into picture. I just explain it again for your concept to be clear, that H is probably U plus PV. So whenever we make this difference, this balance, that H1 plus V1 square by 2 is H2. So within the H, this U and PV adjustment will be made by the friction. That means whether friction is there or friction is not there, that will depend upon this distribution within U and PV. They will adjust. If friction is there, U will be more, the internal energy will be more because of the friction, whereas where PV is less, the reverse is there. If there is no friction, this U will not be changed, because the internal molecular energy will remain same because of the temperature, and PV will get as proportion to the H, change in H. So therefore it is the conversion from U and PV that will depend upon the friction, but H1 minus H2 is V square by 2, or H1 plus V1 square by 2 is H2 if the velocity is 0, or any other velocity may be there. This is a steady flow energy equation which is independent of whether there is friction or not. This is a recapitulation of the total pressure and the total temperature. Now come to the point, if we consider the point 1, that is the inlet to the impeller at point 1, where we have got the total temperature is the total temperature T1T, and if we get a total temperature T2T. Now let us, before that, let us consider this way, let us consider this way, that Okay. Let us consider this way, that if T2, T3T is the total temperature at the outlet of the compressor, at the outlet of the compressor, that means at the outlet of the diffuser. Then T2T, if we write T2T is the total temperature or the stagnation temperature, total temperature at the outlet of the diffuser, since there is no at the outlet of the impeller, that is outlet of the compressor, that means at the outlet of the diffuser, at the outlet of the diffuser, then we can write T2T is equal to T3T, because the total temperature remains same, because there is no energy added in the diffuser. So, therefore, we can write that energy added per unit mass, that work done per unit mass or energy added per unit mass is equal to Cp, specific heat, into T3T minus T1T, or is equal to Cp into T2T minus T1T. Clear? That we can write very well this one. Cp T3T minus T1T is equal to Cp T2T minus T1T. Now, this becomes equal to what? Again, E by M we have got is equal to psi sigma U2 square. So, therefore, what we can write now? We can write, we will come to this afterwards. I will do something else here, we will come it afterwards. Before that, I will do something here, that we ultimately get E by M is what? Now, here E by M is what? Again, E by M is this, yes. Then we can write from this we can write Cp, let us write here T3T minus T1T is equal to psi sigma U2 square. So, therefore, we can write simply T3T by one step is equal to, this becomes 1 plus psi sigma U2 square by Cp T1T. So, a ratio of temperature T3T to T1T we get. Okay. Now, this is the T3T outlet temperature, this is the T1T. Now, you come to this, if this is the 1, now if we have an isentropic expansion, we get a point here. This is the P2T. Okay. So, therefore, we can get this point here. Sorry, this is not P2T, I write it is, this is the final pressure of the compressor, that is total pressure of the compressor, P3T. This is, sorry, P3T. Now, here is the point, this is the isentropic compressor. The actual T3T is not at this point, because the actual process is not isentropic. This point we denote as T3T dash, that means this temperature. So, therefore, if this temperature I know, then I can write the pressure rise, the expression for pressure rise, which I am interested to know, T3T dash divided by, this is T1T, that the inlet temperature to the compressor, T1T to the power gamma by gamma minus 1. This is the isentropic process relation between pressure and temperature. But actual T3, that is the temperature at the outlet of the diffuser, that is outlet of the compressor, is different from that of the isentropic process. Actual process is not isentropic. So, what will be the actual process? Actual process will not be vertical. So, there may be two options, the process may be like this or process may heel towards left. As we know that the adiabatic process, that means a process without heat transfer, but with frictions or internal irreversibility, entropy always increases. What is an isentropic process? Isentropic process is a process which does not have any heat transfer with the surrounding. The system does not have any heat transfer with the surrounding. At the same time, there is no irreversibility inside. There is no friction, even no heat transfer within it. Temperature is almost uniform at any instant, so that internal dissipation or internal irreversibility is 0. At the same time, there is no heat transfer, external irreversibility is 0. So, process is totally reversible, and at the same time adiabatic, entropy remains constant, that you know from thermodynamics. But if the process is adiabatic, but you cannot avoid the friction, so this is known as adiabatic process with internal irreversibility, for which we know from the principle of increase of entropy that entropy always increases because of the internal irreversibility. So, therefore, the actual process is shown. It is recapitulation of your thermodynamics. So, actual process is shown like this, that is T3 T. So, therefore, this temperature lies here. So, therefore, this is the actual temperature. Here we define a terminology known as isentropic efficiency of compression, isentropic efficiency of compression, which is defined as the ratio of these two temperatures in a way that T3 T dash minus T1 T divided by T3 T minus T1 T. Actually, there is a Cp, this cancels out. This ratio is what? Physically, that it is the actual work that is required divided by the ideal work. Actual work is always more, T3 T is more than that. This is because of the friction, and temperature increases because of the increase in the entropy due to internal irreversibility. So, therefore, actual temperature rise can be written in terms of this, in terms of the isentropic efficiency eta C, isentropic efficiency of the compressor eta C. So, therefore, what we can write T3 T minus T1 T is, therefore, we can write is eta C into Cp into what is this T3 T dash, this is eta C is equal to this. So, T3 T dash we can write this is T3 T dash. So, 1 eta C, that means we can write now Cp T3 T minus T1 T is this. Here we have as T3 T dash by T1 T is this. Therefore, we can relate this T3 T dash by T1 T in terms T3 T minus T1 T in terms of this through this eta C, and we can find out the pressure rise. However, today's time is over. I think I will discuss it tomorrow. Okay, next class. Thank you. Okay.